What specific problem does your method aim to solve regarding LLMs, and how does it fit into the larger context of AI research?
Our method specifically aims to address the problem of underthinking in o1-Like large language models, LLMs, which refers to their tendency to prematurely abandon promising lines of reasoning, particularly when faced with challenging problems. This behavior leads to inadequate depth of thought and frequent switching between different reasoning strategies, resulting in incorrect responses. By introducing a decoding strategy with a thought-switching penalty tip, we encourage these models to thoroughly explore each line of reasoning before considering alternatives, thereby improving their accuracy without requiring additional fine-tuning. This work fits into the larger context of AI research by enhancing the efficiency of reasoning processes in LLMs, aligning their cognitive behavior more closely with human-like deep thinking, and ultimately contributing to the development of more intelligent systems capable of tackling complex tasks effectively. Our findings highlight the importance of not just generating correct answers, but also ensuring that the reasoning processes leading to those answers are robust and efficient.
Can you describe how the proposed decoding strategy with thought-switching penalty tip works? Please illustrate it step by step, including the adjustments to the logits and the impact on model behavior.
The proposed decoding strategy with thought-switching penalty tip works by modifying the logits associated with tokens that indicate thought transitions, thereby encouraging the model to explore each reasoning thought more thoroughly before switching to another. Step 1 involves identifying tokens associated with thought switching, such as alternatively, and creating a subset of these tokens, denoted as #V. In Step 2, the logits for these tokens are adjusted. If a token at position T is a thought-switching token, its logit Z_TV is reduced by a penalty strength parameter, alpha, making it less likely to be chosen. Step 3 involves determining the duration of this penalty, controlled by a parameter, beta, which specifies how many positions from the start of a thought the penalty remains active. This adjustment results in a new probability distribution for token generation, which prioritizes the continuation of current thoughts over switching. The impact of this strategy is that it leads to improved accuracy in model responses, as it mitigates underthinking by promoting deeper exploration of reasoning paths, ultimately aligning the model's behavior more closely with effective human problem-solving processes.
Provide a concrete example from your experiments that demonstrates the phenomenon of underthinking in LLMs. How did the model's switching behavior affect the final outcome?
In our experiments, we observed a clear instance of underthinking in the o1-Like LLMs when analyzing responses to challenging math problems. For example, in one case, the model initiated a correct interpretation by recognizing that the given equations resembled those of ellipses centered at specific points. However, instead of thoroughly exploring this promising line of reasoning through further algebraic manipulation, the model abruptly shifted focus, leading to the generation of approximately 7,270 additional tokens without arriving at a correct answer. This frequent switching behavior resulted in the model abandoning a potentially correct solution, ultimately concluding with a guessed answer that lacked support from a comprehensive chain of thought. This example illustrates how the model's tendency to switch thoughts prematurely directly contributed to its failure to reach an accurate conclusion, highlighting the inefficiencies associated with underthinking.
What are the key theoretical or practical benefits of using your proposed method compared to existing approaches in tackling underthinking in LLMs?
The key theoretical benefit of our proposed method, the thought-switching penalty tip, lies in its ability to systematically address the underthinking phenomenon in o1-Like LLMs by encouraging deeper exploration of reasoning paths before switching thoughts. This contrasts with existing approaches that primarily focus on maximizing output likelihood without considering the depth of reasoning. Practically, TIP has demonstrated consistent improvements in accuracy across challenging test sets without requiring additional model fine-tuning, as evidenced by our experimental results with the QWQ32B preview model. By penalizing tokens associated with thought transitions, TIP effectively reduces the frequency of premature thought switching, leading to more efficient token utilization and better alignment with human-like problem-solving processes. Overall, our method not only enhances the model's reasoning capabilities, but also provides a quantitative framework to assess and mitigate underthinking, which is a critical aspect of improving LLM performance on complex tasks.
How did you validate the effectiveness of your method during experiments? What were the specific datasets used, and how were performance metrics computed?
We validated the effectiveness of our method, specifically the thought-switching penalty, TIP, through experiments conducted on 3 challenging datasets, Math 500, GPQA Diamond, and AMY 2024. The Math 500 dataset consists of high school math competition problems. GPQA Diamond includes graduate-level multiple-choice questions in various scientific domains, and AMY 2024 tests mathematical problem-solving across multiple areas. Performance metrics were computed using both accuracy and a novel underthinking metric, which measures token efficiency in incorrect responses by evaluating the proportion of tokens that contribute to reaching correct thoughts. Our experimental results demonstrated that employing TIP consistently improved accuracy across all test sets, indicating that the method effectively mitigated underthinking issues in o1-Like LLMs. The results were reported as pass at 1 accuracy, showcasing the model's enhanced performance without requiring additional fine-tuning.
What were your most significant findings regarding model performance after implementing TIP, and how do these results inform our understanding of underthinking in AI systems?
After implementing the thought-switching penalty, TIP, our most significant findings indicated a consistent improvement in model accuracy across all challenging test sets, demonstrating that TIP effectively mitigates underthinking issues in o1-Like LLMs. Specifically, the QWQ32B preview model showed enhanced performance, with accuracy gains observed as we adjusted the penalty strength and duration, particularly achieving the highest accuracy with a penalty strength of 3 and a duration of 600. These results suggest that by discouraging premature thought switching, models are encouraged to explore reasoning paths more thoroughly, leading to better problem-solving outcomes. Furthermore, our analysis revealed that underthinking is characterized by the model's tendency to abandon promising reasoning paths, which TIP addresses by promoting deeper engagement with initial thoughts. Overall, these findings underscore the importance of refining cognitive processes in AI systems to enhance their reasoning efficiency and accuracy, particularly in complex problem-solving scenarios.